on this computer. Okay. Good. So now let me share some information regarding the course. So the course, as I said to you previously, let me check on the website. We will have one midterm and one final. Okay. The midterm is scheduled for 21st of February. Is a take-home exam. So we are not going to stay here for 3 hours. You will get your questions, which will be maximum 6 questions. You will have 48 hours to answer to those questions and properly scan them as a single PDF file and sending back to me, okay? Not to your TA. So midterm and final, both of them, they should be a single PDF, and both of them, they should be sent back to me within 48 hours of the posting. I will send a private message to everyone. So there will be no question regarding when it will be posted, when I should return it back. So everything will be clear on even questionnaires, okay? So that will be 21st for your midterm. Please mark it in your calendar. You will have 48 hours to return it back to me. Your final is scheduled for April 23rd. Okay? The same scenario. You will have 48 hours. April 23rd. Okay? Is on the website. Is written clearly on the website in the lower, just before the Zoom link. Okay? So just before the Zoom link, there is a box which you can see both dates. Okay, please mark your calendar. There is no need to tell you what is the academic fraud, what issue you may have it during the course, because all of you, you are graduate students, so you are really mature. And you know that hereafter, you should trust to yourself. So I will not really raise any of those questions. So please be aware of the fraud, academic fraud. Try to answer to your question by yourself, not, of course, I mean, sometimes you need to consult other people, but please try to think first by yourself. And then if you have any question, either ask me or ask your TA or ask your colleagues, okay? Any question on these? We will have 12 lectures and 1 week, which is a study week, reading week. I will not ask you any question during the reading week, and you will be prepared for the exam. We will have 12 lectures of 3 hours, and we will try to reach and study 6 chapters from those books that I posted there. So the main one will be the book by Marlon Scully and Zuberi, which is the quantum optics book. As I say on the website, we will try to cover chapter 1, 2, 3, 4, 18, 20, and 21. And in the same time, we will also visit the first book on quantum optics by Ronde Loudon, which is the quantum theory of light. And we will study chapter 1, 3, 4, 5, 6, and 9. So there is overlap between those 2 books and those chapters that I mentioned that to you. So, and we will not consider any light matter interaction. So it will be only about light. This is the subject of the book. So, sorry, the course, which is a quantum theory of light. So, for the light matter interaction will be the next course that will be, I think, will be offered next semester. Any so far so good? Any questions? Each 2 weeks there will be homework. will be 4 questions to 8 questions, depending on the length and the time that you may spend on these. So, and you will have 6 assignments in total. Okay. Now, in terms of grading, activities which involves also assignments will cover 20% of total grades. All right. Midterm 30%, and final will be 50%. Okay. So 20 for assignments, 30 for midterm, and 50 for the final. So we have another person joining the group, which is Valerio. Any questions, guys? Is everything clear for in terms of expectation, in terms of the course assignment? If you have any concern, just let me know. Okay, excellent. And note that we are going to learn quantum optics together. Someone is speaking. Valerio?
Sorry, yes.
No worries. So I think you were in late. No worries at all. Just would you please introduce yourself?
Yeah, my name is Valerio Kashimanna.
With whom are you working with, and on which subject?
Sorry?
Who is your supervisor, and what is your thesis subject or research activity subject?
Yes, my thesis supervisor is Professor Kabata Shami, and the topic is quantum tomography.
Excellent. So Valerio, just to review, previously all members, they introduced themselves, and we had a little bit of chat, and I asked them to have a permission to record the talk, and the talk will be on a private channel on YouTube, but will be available maybe to everyone on the website. So do you have any problem with that?
No, not at all.
Okay, excellent. And regarding the course, we say that we will have 6 assignments, and in total we have 12 courses. We will cover 6 chapters from either book, because they have overlaps, the 2 books, and 20% will be for assignments and class activities, 30% for a midterm, and 50% for final. Midterm is on February 21st, and you will have 48 hours, and final will be on April 23rd, and you will have 48 hours. It's take home. And of course, you should be aware of academic fraud, which is posted on the website and also on the university website. I will encourage you, if you are new at the University of Ottawa, please read them. Okay? Excellent. So now we will start to do, okay, so I have to give the permission to myself to share the screen. So now we will start the course. The first lecture will be, let's say, reviewing what's going on and what we have learned during electromagnetism or electrodynamics. So far, we try to in physics. I mean, during your undergraduate or let's say graduate program, you learn about dynamics, and essentially you assign coordinates to an object, and on the top of these also you had time as a parameter. But however, in relativity, we learn that essentially we have to work with the covariant form. Okay, is fine, I think, the size. which is ct and the vector of x. And no, I think needless to say that x is the three coordinates is x, y, z, or r, theta, phi, or rho, phi, and z in different coordinates. And c is the speed of light in vacuum, and t is the time. So essentially, general and special relativity by Einstein say that you can unify the coordinate and time, and essentially there is always a transformation, which is a Lorenz transformation, which essentially can link any coordinate that you may have to another one. So if you call this that's x mu, then you can link that to another coordinate of x prime, let's say alpha. And essentially, this can be done by a Lorenz boost, which is given by this lambda, and x prime alpha is given by lambda alpha mu x mu, where lambda mu nu is given by, if I recall well, that should be identity matrix, assuming that the boost happens along x direction. Then that should be gamma minus gamma beta minus gamma beta and gamma, and the rest is 0. Okay, so now I assume that the boost happens along x direction. So this is x direction, this is y direction, and that's a z direction. So let's call it prime, just to be clear. And that's x, y, and z. And sorry, y and z. And we assume that the boost happens along this direction, which is given by velocity of v. All right. Okay. So then beautifully we learn that physics essentially are the same at different coordinates. Just you need to link them together. And that was the beauty of relativity. And note that also when you define the x mu, then you can also look at the derivation with respect to x. So you can look at the derivation with respect to mu, which essentially we define it as derivation with respect to x mu, which is given by ct, and derivation with respect to x, which is, let me write it down as a gradient. So those are the derivatives in a quariant form. And we know that in order to define any product, you also have to look at the metric of the space. So essentially, we are looking at the metric of Minkowski. And the simplest way that we can see it, G mu nu, I will define it as 1 minus 1 minus 1 minus 1. For those people that they have taken the course of electromagnetism with me or electrodynamics, they know very well that I prefer to assign -1 to the time. But anyway, now I am doing this just because of the conservation of energy, looking at the positive energy and etc. Good. And then I know that always I can link the two forms of these and these together by looking at the metric. So this transformation can be done by the metric G alpha mu, and then I will get derivative with respect to alpha. And from this, I will find I find out that derivative with respect to alpha is given by x alpha which is given by derivative with respect to ct and minus gradient. So who has problem with the covariant form? Who has not seen these previously? Don't be shy.
I have not seen this.
I haven't, Ibrahim.
Who? Okay, can you? Because I cannot see all of you guys. Can you?
Jeremy.
Jeremy. Okay. Kevin as well.
Yeah. And Josh.
Josh. Okay.
And okay.
Okay. So, do you have any problem with understanding those equations, or should I introduce them?
No, this is fine for me at least.
Jeremy?
Okay.
I'd like an introduction.
Okay. Good. Let's go back. Haha. So, this is an introduction, guys. You can take a break. Essentially, when we look at the coordinates, we have three coordinates essentially. So we call them x, y, and z. And on the top of these, we have time. So if we look at physics at many different perspectives, for example, if you look at the Newton's equation, or you can look at the Hamilton equation, Hamilton-Jacobi, or Lagrangian form, or Maxwell equation, always you deal with derivative with respect to x, derivative with respect to y, derivative with respect to z, and also derivative with respect to time. So time previously was considered as a parameter, and it was assumed that it's different from coordinates. So it's different. Time was considered as a parameter, and not a part of the coordinate. So, for example, if you look at Newton's second law, which is F is equal to ma, all right? Here, what you have, you essentially have, when you define the force, when you find the force, if the force is constant, for example, then what you will get m second derivative of, for example, x with respect to time along x hat m dy dt squared plus m d2 squared is equal to f. And from this side, you will find that f has three components: x hat, y hat, and z hat. And from this, you will get three different equations, three different equations of motion. And from this, you will get x, for example, is given by, you have to take the integral, essentially. Let me do that. M d x dot dt squared is equal to fx, and until m dy dt squared is equal to fz. And here, then you have to take the integral, then you will get dx dt is equal to f x divided by m integral of dt plus a constant, and then another integral, then you will get x is equal to integral of fx m dt prime plus integral of c dt prime plus d. So then you will get an equation which is essentially x is given as a function of time, and then you will get the same story, which is y is given as a function of time, and z is given as z as a function of time. So in all of those equations, what you have coordinates which they are time dependent. And if you sum them up together, then you will get an equation which is r is x as a function of time, x hat, y as a function of time, y hat. Plus z as a function of time, z hat. All right, so, and then what people, they understood, they say, okay, if I change from one coordinate to another coordinate, how those equation of motion will change. This is what happens. For example, Kevin, you can have a car and you can drive, and both of us, we will see that an apple is falling down from a tree, okay? And we are writing that equation from two different observers, and we compare the equations together. We can do that. Essentially, this absolutely is not a problem. However, what was the main issue is that there were some equations which they were changed upon changing the observer. And explicitly, when you go with speed which is higher than certain value or close to the speed of light. And then Einstein thought that, okay, so time also is a part of the coordinate, and he gathers them together as x and ct, and then defines any of those observers to be at different locations and different boost which happens to those coordinate system. So for example, if you are moving on a car, you are inside of a car and you are moving with a certain velocity, then there is a transformation from my coordinate to your coordinate, which is different from Galilean transformation, and that is given by a boost in the time-space coordinate. So that was the general idea. So maybe I went too fast at the beginning. I didn't know that maybe some people, they have no clue about the relativity. But essentially, I always prefer to start with relativity, even we deal with the quantum optics, because there are a lot of hints there which is hidden from other perspectives. So that was the reason that we started from this. And we say, okay, now assume that now what we have also the coordinate, which is x, and we have ct as another element of the coordinate. We call these 4 vectors. It's 3 for the coordinate and 1 for the time. All right, and usually we use Greek letter to identify if whether we are dealing with the 4 vectors or we are dealing with a 3-dimensional vector. If we use a Latin, we are using, let's say I, J, K, whatever, we are referring to the 3 coordinates. When we are using the Greek letter, we are referring to the time as well. So we have 4 coordinates essentially. So whatever happens between, let's say, observer number 1 and observer number 2 is given by a boost which links the 2 coordinates together. And this boost, if we assume that, for example, since Kevin asked the question, if Kevin is moving on a car, okay, and he drives along a certain line, doesn't go left and right or up and down, it goes straight. And then if I assign that coordinate to be along x direction, then simply the Lorenz boost is given by this term that I have written here. Then there is something more in the notation. When I have an index which is repeated, like this one, I have mu, which is repeated here. It means that there is a summation over that index. So indeed, what I have written here is summation or of lambda alpha mu x mu, which mu is changing from 0, 1, 2, and 3. 0 is assigned to the first term. We usually call that x0, and the rest we call them x1, x2, and x3. So this means that the summation will happen over the subscript of mu. Okay. Better or okay. Good. And in so if you remember, we have always, let's say, E dot E, A dot B, A dot C. When we are dealing with dot product, which we are reducing from a vector, we are changing two vectors to be a scalar quantity, then we have to define the linear product. And in order to define the linear products, you have to also define the metric of the space. And the metric of the space that I define here for the Minkowski metric is given by this term. All right. So I will erase the rest, guys, and I will follow the discussion that we had. Any questions? Welcome, Mahtab. Okay. All right. So we are going back to the relativistic regime.
Thank you.
Yes. There was someone asking a question? Okay. So now, in order to define the linear product, as I say, you need to look at the metric, which the metric is defined here, and you have to look at the dual space. So CT and X, there are 4 vectors, and from these 4 vectors, we are defining another set of vectors, which we call them dual space. Okay. So for those people that are familiar with the quantum notation, one of them is look like bra, the other one is look like cat. So in order to define linear product, you need bra and cat. So if you define cat, then you have to define the metric in such a way that the linear product will be positive value. And then in order to do so, you need to define the metric. So the metric is given here. So this is look like x mu, which I am writing here. This is look like bra notation is given by g mu nu of x nu. So it means that the summation is over nu value. And g mu nu, of course, is an inverse, which essentially is given by the same metric, because this is not coordinate dependent, is easy to find that. So that will be given by CT and minus X. So now if you look at the linear product of x mu, which has 4 terms, then you are dealing with CT squared minus X squared. Or if I want to be careful, since we have X, let me write it R squared. This is a constant, remember. This is what we call it covariant form. Okay. In the same manner, we can find what is the derivative with respect to mu, which is as what I said, is derivative with respect to x mu, then is derivative with respect to ct, and minus gradient. And then I can look at the invariant form of these, which is derivative with respect to mu, derivative with respect to mu, which is given by ct squared minus Laplacian. If I want to write properly, maybe it's better if I write this one as nabla nabla, which is 1 divided by c squared time derivative minus Laplacian plus minus Laplacian, which we call these D'Alembert. I define this. So note that D'Alembertian is invariant. What does it mean? That if you change from one coordinate to another coordinate, the only things that you have to change is label t with t prime, Laplacian with Laplacian prime. That's all. Is invariant under Lorenz transformation. So it means that Joshua, myself, Jeremy, Kevin, Victor, and all people, we will have the same equation when we are applying a wave equation to a different system. So wave equation is invariant under Lorenz transformation.
I have a quick question, Dr. Karimi.
Absolutely. And please do not call me Dr. Karimi. You can call me
Sure.
Ibrahim.
Ibrahim.
Yes.
I've never seen the colon equal sign thing you're doing before.
Oh, sorry.
What does that mean?
Yeah. So this means define.
Define. Okay.
Yeah. And the same.
Yep. Okay.
I'm sorry. I'm old-fashioned mathematician.
That's totally okay. I've just never seen it before.
Yeah. So when I define something, I will go with this way. Okay.
Sorry, Abraham. Just
Yes.
to clarify, the subscript versus the superscript on the vectors. This is just like the conjugate space, like a bra or a ket.
Yes, it looks like dual space. So one of them is a real space, which is what I tried to explain at the beginning. One of them is a real space that you have it here. Do you see?
Yeah. Okay.
And the other
Yeah.
one is a dual space.
Okay. Yeah.
Okay.
Yeah. Thank you.
Of course. Any other questions, guys? Eric has used these equations a lot, right? Eric?
Yes. Sometimes with results. Sometimes.
Yeah. Okay. So good. Now let's go and see what else can we learn about them. Remember, this quariant form it's just amazing. It's beautiful. There is a reason that I'm telling you, because I want you to think, and I want you to understand the deep physics behind of all those equations. Look, I don't want to really teach you what is the basic of relativity or basic of electromagnetism or electrodynamics. But remember, when I have a coordinate which is x mu, which is ct and x, or what I say that you can even label it by xi, depending on the way that you think. Always I can find other four vectors. So what is the first trivial things that you want to build up after having coordinates? So we have coordinates. Then from the coordinate, what usually we learn in the course of dynamics to build up?
Velocity.
Velocity. Excellent. Okay, let's build up velocity. What is velocity? Derivative of displacement over the time, right? The rate over the time. So first of all, you have to look at the derivative of x mu. What is the derivative of them? Is c dt and dx. Excellent. What is the invariant term that you may have? It is dx mu. Dx mu is invariant. What does it mean? That at different coordinates, you will see the same physics. You will see being identical. Let's build up that. So d mu will be given by c squared dt squared minus, remember, one of them is lower index, is a subscript of x mu. So then that one will be dr squared. All right. So let me write down dx mu will be given by c dt and minus dx. Remember this. So that is invariant. So it means that two different coordinates, they will see the same physics. So I will write it for different coordinates. C squared dt squared prime minus dr prime. All right. So now I assume that one of the coordinate, in one of the coordinate r prime is 0. So the time is at the coordinate of, let's say, location is 0. Then I will label that with proper timing, which I will call it with the tau square. And this is the proper time. Why I'm doing so? Because I want to build up velocity. But in order to build up velocity, as we discussed, we need to have certain time, which is unique for all of them. Let's do that. Then let's find c squared dt squared minus dr squared is equal to c squared d tau squared. Then d tau squared will be equal to dt squared 1 minus dr squared divided by dt squared divided by c squared, which is dt squared, and that is 1 divided by gamma squared. Gamma, as we say, and we know very well, is 1 minus v squared divided by c squared. And you have seen gamma and beta in the boost. Remember, also beta is v divided by c. So that is given by 1 divided by square root of 1 minus beta squared.
Yes.
Yes.
I think I missed with this point. Like, why do you treat dr prime as 0?
I say that the timing is at location which I choose on the look. I have two coordinates.
Mm-hmm.
One of them can be moving with respect to the other one.
Yeah.
The other one can have time anywhere. Okay. Now what I do for another one coordinate, I choose the time is at r equal to 0. There is no location changing.
Okay, got it.
Okay, dr is equal to 0, so I'm not moving my watch with myself.
Okay, got it.
Okay.
So one is with respect to the other. One is like a stationary, and other one is moving, right?
The other one is moving. Yes.
Got it. Thank you.
Okay. I want to find out what they call it proper time, which means that the location is fixed for the time. Okay. So from here, what I find that d tau is given by dt divided by gamma. I assume that the time is going to be positive, is not negative. This is what I get. So having video on is so amazing. I see that 2 people already left. Okay, Joshua and Jeremy. Okay, so now, since I find the time, now I can define velocity. So velocity, or let's go with u, it maybe is better or proper. U alpha is given by dx alpha divided by the proper time of 2. Now I define the proper time. So let's do that. Then I will get c dt and dx alpha. And proper time will be gamma divided by dt. If you simplify this, you will get gamma c and dx divided by dt, which will be velocity of v. All right. Good. This is the velocity. And from velocity, what you do? Joshua mentioned that to me, that Ibrahim, let's build up velocity. And now I have 4 vectors of velocity. And the 4 vectors are given by gamma c and gamma v. Someone wants to speak? No one? Okay.
Acceleration? I don't know.
No.
Or-
You can
or
build up
momentum.
acceleration, but acceleration usually does not give something very meaningful.
Energy?
What is the second form? I mean, you are close. What is the second form of Newton's law?
Or momentum?
Exactly. Built up momentum. P alpha. How do you build up momentum? Mass time velocity. And this mass is m0, which is the rest mass times velocity of u alpha, which is gamma m0c and gamma m0v. Remember, this m is the rest mass. Okay? We call these 4 momenta. And that is given, we call these pi or p. And this term, not surprising, is energy divided by c. And that is p, the 3 momentum, or three components of linear momentum. All right, so now let's build up the dual vector of P alpha. So what you have to do, you have to apply the metric, and what you will get E divided by C and minus P. And P alpha is invariant. What you will get from is E squared divided by C squared plus P squared. This is invariant. So it means that two observers, let's say Arman and myself, we will see the same physics, although Arman may see that that particle doesn't have the momentum. Maybe I see that that particle has momentum because maybe I'm in my coordinate the particle is moving, but maybe in Arman's coordinate the particle is not moving. So when it does not move, then it doesn't have a linear momentum, but it has the energy. So, for example, in the same way that we look at the proper timing, you can look at the total energy. So in one coordinate, the particle doesn't have a linear momentum. In the other particle, either coordinate, the particle has momentum. Oh, sorry, there is a minus sign here. Here is minus sign. My apologies. And the other one has linear momentum, which is minus p squared. Then from this equation, I will get that E squared is equal to E0 squared plus P squared C squared. You remember this equation, right? From modern physics. Any questions? No? Beautiful. So now we do have almost everything from classical dynamic. But we know that, look, classical dynamic just deals with motion of particles. But we have another field of research, which is classical electrodynamics, which what means we have electric charge and we have currents, which they will induce forces. And then from those forces, you will have an object which might move or might have a specific dynamics. So in order to define electric field and magnetic field, you need to know what's going on with the charge density and current density. Do you remember this? So we need to know rho and we need to know J. Here in the relativistic regime, we have 4 currents, which they call it J alpha, which is given by 0 and J. Rho is charge density, and J is the current density. So this is Jx, Jy, and Jz in the Cartesian coordinate, and that one is a rho. Okay? Let's look at a covariant form of this. So do you remember that I mean those people that they have taken the course of electromagnetism with me? So I always give them a puzzle. The puzzle is that you have 2 observers. Let's say David is one of my observer and myself is another observer. And in my coordinate, which is I am fixed with respect to a charge, I see that that charge has only electric field. But David is moving inside of a car with a certain velocity. In David's perspective, David sees that this charge is moving, right? In addition to Coulomb force, there will be a magnetic force as well. So then what's going on here? How is happening that the electric and magnetic field depends on the coordinate? So if I'm fixed with respect to a charge, I will see only electric field. When I'm moving, I will see electric field and magnetic field together. Okay, so that's a relativistic problem, and it can be resolved easily by looking at the Lorenz boost and Lorenz transformation, and you will see that electric field and magnetic field, they are just only the same. They are two different forms, but they're identical, okay? So there is no problem with that. But remember, when we deal with these two, then we need to know J and rho. So let's build up a covariant form of this. So look at the derivative of J alpha. Of course, I can build up J alpha. So what is J alpha? Lowercase is subscript of alpha, which is C rho minus J. And then I can look at the derivative of alpha of J alpha, which is invariant form. And what I will get derivative with respect to Ct of C rho minus divergence of J. So divergence of J minus, derivative with respect to time of rho minus divergence of J is equal to constant. What is this? Who remembers this equation?
Continuity equation.
Exactly. Is the continuity equation. So it's an invariant form. It says to you that there is no charge that can be created and no charge will be annihilated. The moving of the charges around will produce currents. That's all. All right? No questions? Good. So from the charge, now going up, what do we have else? From the charge, if you remember, I don't want to go into all of those deep calculation. From the charge, we built up, let's say we fix the gauge, everything is fixed. We built up the potential. We find what is going on with scalar potential. And from the current, we built up the vector potential. What are those for vector potentials? A alpha is given by phi divided by c. This is a scalar potential, and this is the vector potential. Scalar potential, and this is vector potential. Look, C, you see that C always appearing in the J, in A, in momentum, in velocity, in 4 coordinates. That happens just to give you the possibility to have the same dimensionality. So A and phi divided by C, they have the same dimension, same units, essentially. Good. Now let's build up another invariant form. So let's look at derivative of alpha of A alpha. What is that? Is derivative of phi divided by C divided by Ct minus divergence of A. All right. So that will be 1 divided by C squared, phi divided by time minus divergence of A. What is this? Let me write it in a form that maybe you will like it more. Mu 0 epsilon 0 phi divided by time minus divergence of A. Who remembers these? Joshua?
I'm a bit slow today, but it's given me some scalar wave equation vibes.
Yeah. Let me ask, embarrassing some of students that they have taken the EM or electrodynamics with me. So who should I start, Kate or Eric?
I remember seeing it, but I don't remember the name. I'm sorry.
Isn't this one of Maxwell's equations?
You can obtain it from Maxwell equation, but it's not Maxwell equation. Come on.
It reminds me of the Lorenz transformation, but
Exactly.
okay, well, I'm glad that was mostly a guess.
Yes, it's a gauge. It's a gauge that you have it for divergence of A and potential. It's a Lorenz gauge. Lovely, fantastic. Do you remember the other gauge, Eric? So let me ask someone else. So who remembers the other gauge?
Coulomb gauge.
Coulomb gauge. Who is? Arman, yes.
Yeah.
Do you remember what's the form of the Coulomb gauge?
I mean, is it just minus the gradient to the potential?
Is a divergence of A is equal to 0?
Yeah.
Exactly. So remember we have 4 gauges. So I don't want to talk about the other 2 because no one really uses. But this is a constraint that you have it when you want to fix the relation between A and phi. Do you remember that we say that the potential, they have a relation among themselves, and you have a freedom to choose the potential. But what is the freedom? You have to fix it. And this fix of among the potential is called the gauge. Okay? And we use them sometimes just to understand or simplifying the equations. So I remember in the course of electrodynamics, I solved problems for different gauges, and you will see that in one gauge is extremely simpler, and in other gauges extremely difficult. Okay, so it's just freedom of choice that you have it here, and you will see that beautifully you can get it from electrodynamics, from Lorenz transformation, and you can easily move from one coordinate to another coordinate, and you will find out what is the relation between the potentials. The relation between potentials is extremely simple. It's given by Lorenz boost, indeed. So if you go from, just as an example, if you go from one coordinate to another coordinate, do you remember that I gave the example that David is moving in another coordinate? If I know the potential, which means that I have phi and A in my coordinate, I want to know what is going on in a David's coordinate, phi prime and A prime, then always there is a Lorenz transformation which links these two together, lambda alpha beta. And this is given by A alpha prime equal to lambda alpha beta, A beta. So is the boost, if the boost is along x direction, that is given by gamma minus gamma beta, gamma, and the others will be 1, 1, and the rest will be 0, multiplied by phi divided by c, ax, or a1, a2, and a3. And from this, I will find out that phi prime divided by c is given by gamma phi divided by c minus gamma beta a1, and a1 is given by minus gamma beta phi divided by c minus plus gamma a1, and a2, a3 will not change. Okay, So this is the beautiful way of linking the coordinates together. And whenever you know the potential in one simple coordinate, you will find out what's the potential in other coordinate which is moving. Good? Beautiful. Now, let's do a little bit of mathematics and understand what's going on with electromagnetic tensor. So we know the potential, and from the potential we can build up electric field and magnetic field. The way that we build up electric field and magnetic field is given by derivatives, if you remember. So from guys, if you have written down, then I want to go a little bit down and writing a new line. I will keep it here. So when I know the four potential, from four potential, I can find the dual potential, which is A alpha, and then I will find out electric field and magnetic field. Which is derivative with respect to alpha of A beta minus derivative with respect to beta of A alpha. And of course, you know what is A alpha, a derivative with respect to alpha and derivative with respect to beta. We already found it. And you know how to find the dual space of the four potential. It's just by applying the metric, which A alpha is given by phi divided by C and minus A. And yes,
line that you wrote, is that a minus sign or an equal sign between the derivative of alpha?
It is minus sign, definitely.
Okay.
That shows. Look, you will see it in a few minutes. But for those people, they know that Maxwell equation. You know that if you look at the bx is given by curl of E, the x component. So usually you have two terms. And the same story for electric field and the different component of electric field and magnetic field. So I don't want to really write Maxwell equation because I want to drive Maxwell equation from those expressions. Because we should not really worry now about anything because everything is set with a relativistic regime. So everything is fine and follows the Lorenz transformation. So the physics is the same from different observers' perspective. Okay, any questions? No? So if you do a little bit of mathematics, and if you look at different component of this, first of all, what is F alpha alpha? Ben? What is F alpha alpha? If I set beta equal to alpha, what is happening between this equation?
Wouldn't the beta derivative just go to 0?
Exactly. That will be 0. Good. So alpha and beta, they will change from 0 to 3 because we have 0 for the time and 3 for the other coordinates. And whenever alpha and beta, they are equal to each other, then that term will be 0. So definitely there is a matrix of or tensor of 4 terms. 0, 0 is 0. 1, 1 is 0. 2, 2 is 0. 3, 3 is 0, as Ben says to us. What is going on with F01? Who voluntarily want to help me? Valeria, do you want to help me? let's do it together. Okay. So I will replace this with 0, and that one will be A1 minus derivative with respect to 1, and that will be A0. So let's write it down. What is the derivative with respect to 0? Lowercase will be derivative with respect to CT. What is A1? A1 will be AX minus derivative with respect to X. What is A0? Oh, that has a minus sign, I think. And that will be pi divided by C. Is that true?
Yeah.
Excellent. So let's write it down. So it will be minus 1 divided by C, AX divided by time, minus 1 divided by C, derivative of phi with respect to X. So that will be 1 divided by C minus time derivative of AX minus X derivative of phi. What is that? Any idea? This is EX divided by C. Do you remember the EX? E, if I will write it down here, E was minus gradient of phi minus time derivative of A. This was E, and B was curl of A. Good. So now I find that one is EX divided by C. The other one will be EY divided by C. The last one will be A. Let me write it down properly, maybe. And since it's antisymmetric, then the other term will be negative. EX divided by C, EY divided by C, EZ divided by C with negative sign. Then that term is 0. And that one will be minus BZ. And the other one will be BX, I think, or Y. This is BZ because it's antisymmetric. 0. That one. 1 divided by C of X. Papa is minus BY. Then that term is 0. This term is B divided minus BZ, BX, plus BX. Okay. All right. So this is the electromagnetic tensor of F alpha beta. F alpha beta subscript will be just transpose of this one. Okay. So you may ask me, okay, I find 4 potential, 4 currents, and now I have electromagnetic tensor. What is next? Do you want to write the laws that dictates what is the relation between electric and magnetic field and currents? And what I mean, Maxwell equations. Maxwell's equation now is written in this form. Is alpha if alpha beta is equal to mu 0 j beta. Okay. And the other Maxwell equation is given by derivative with respect to alpha of 1 divided by 2 epsilon alpha beta gamma delta f of gamma delta equal to 0. Remember, here beta is a free choice. Here the summation is over alpha. Here the summation is over alpha. And then you have a summation over gamma and summation over delta. Should I erase it? Let me erase that because maybe that interferes too much with you. Okay.
What is epsilon in this case? Or is that
Oh,
an epsilon?
it's a Levi-Civita notation. So any, are you familiar with epsilon ijk?
Yeah.
Okay, it's the same scenario. Whenever the combination is 0, 1, 2, and 3, then you will get 1. All right. When you have odd combination, you will get -1. Even combination, you will get +1. Let me tell you. Write it down, and I will give you an example about this. Okay. Shall I go? Shall I start? Okay. Let's go with, we have about 5-6 minutes, and then we will have a break and we will come back. Next lecture, next hours will be more into EM field. Now we are done with relativistic regime, so we are ready to go with the EM way. So let's look at the first equation. Derivative of alpha f alpha beta equal to mu 0 j beta. Okay, so let's set beta equal to 0. Okay, set beta equal to 0. Let's see what we will get. So this equation becomes derivative of alpha f of alpha 0 equal to mu 0 j 0. What is j 0? Was phi divided by c. Now let's expand this. The left side will be given by derivative with respect to 0, f of 0, 0, derivative with respect to 1, f1, 0, derivative with respect to 2, f2, 0, derivative with respect to 3, f3, 0, equal to mu 0, phi divided by c. All right? Is clear, Henry?
Isn't J0 rho C times
Rho.
rho?
I was about to say that.
J0 is rho times c. My apologies. My apologies. Thank you. Rho times C. Thank you very much. Good. I knew that there is something. Good. What is F00? 0 is 0. All right. F11, sorry, F10. Look, is subscript, is not sorry, is superscript, is not subscript. So that will be the transpose. So that will be given by minus EX divided by C. That will be given by minus EY divided by C. And that will be minus EZ divided by C. True? What is the derivative with respect to 1? Look, is subscript. If you look at the subscript, there will be always a negative sign. So that will be minus derivative with respect to X, minus derivative with respect to Y, minus derivative with respect to Z. Clear? If you forgot this, I will write it down. So if you remember, X mu was CT and X, then we say derivative with respect to mu lowercase will be derivative with respect to X upper. True. And that will be derivative with respect to CT and gradient. Okay. Then what we will get from here, we will get derivative with respect to X, EX, derivative with respect to Y, EY, derivative with respect to Z, EZ, equal to mu 0 C square rho. Okay. C square is 1 divided by mu 0 epsilon 0. And then from here, I will get divergence of E is equal to rho divided by epsilon naught. Good. So exercise for you, homework. Show that derivative with respect to alpha of f alpha beta equal to mu 0 j alpha will give you two equations. Divergence of E equal to rho divided by epsilon naught. Do that by yourself again. Okay? And another equation. The other equation will be given by curl of B is equal to mu 0 j plus mu 0 epsilon 0 time derivative of E. So show that these two equations can be explicitly calculated from this relation. Okay. And on the top of these, show that the derivative with respect to alpha of 1 divided by 2 epsilon alpha beta gamma delta of f gamma delta equal to 0 will give you an additional the other two relations, which is divergence of B is equal to 0 and curl of E is equal to minus time derivative of B. So in order to do this sort of calculation, you have to understand what's going on with the property of epsilon, alpha, beta, gamma, and delta. As I said to you, remember that beta is your free choice. So you have to fix beta by yourself. Okay? So, yeah.
By setting beta as a free choice means can we set it as 0 all the time?
You can set it at 0. It will give you one equation. You can set it at 1. It will give you another equation. If you set it at 2, it will give you the third equation. If you set it at 3, it will give you the last equation. So remember this equation that I have written here, this one. How many equations is?
2 plus 2, 2 equations here, and
the first one is one equation, right?
Okay.
Because it's a divergence, it's a dot product.
Oh,
so it's
yeah.
one equation. The last one
Second, the call operation.
is it's 3 equations.
Okay, I see. Oh, okay, I see. Yeah.
Right? Okay. So then if you set beta equal to 0, it will give you one equation, beta equal to 1, another one, equal to 2, another one, and etc. Okay? Clear?
Yeah, thank you.
Fantastic. Let's look at the property of epsilon. Alpha, beta, gamma, and delta. This is a pseudo tensor, by the way. As I said to you, alpha, beta, and gamma and delta can take any value of 0, 1, 2, and 3. Okay? When they have repeated indices. So for example, if you have alpha, epsilon, 1, 1, gamma, delta, this is 0. Whenever two indices, they are identical, that will be 0. Exactly look like epsilon ijk. They are not 0 if they take sequence. So if is epsilon 1, 0, 1, 2, 3, that will be equal to 1. If 1, 2, and 3, so whatever you have, it is odd combination of 0, 1, 2, 3, alpha, beta, gamma, and delta. If it's an odd combination of this one, that will be -1. If is even combination of 1, 2, 3, 0 is +1. Let me tell you what I mean. So we know that epsilon 0, 1, 2, 3 is equal to +1. Now I'm swapping two indices together. The consequence will be negative sign. So epsilon 1, 0, 2, 3 will be minus epsilon 0, 1, 2, 3. Okay? That will be -1. However, I can swap another time. This is what I mean by even. Okay? You can swap once, or you can swap twice, or 3 times, or 4 times. So anytime that is odd number, that will be negative. Anytime that is even number, that will be positive. So let's swap another time. So it will be epsilon 1, 0, 3, 2. Then is minus epsilon 1, 0, 2, 3, and that is minus epsilon 0, 1, 2, 3, and that is +1. Okay. So we will have 13 minutes off now. I will stop recording, and please be back at 4:20 sharp. Okay, recording. So Eric has a question. He said that, okay, when we look at the invariant form from, let's say, for potentials, then we get Lorenz gauge. Why? Why we don't get Coulomb gauge? Let me give you a hint. Can you hear me, guys? Okay, let me give you a hint. Lorenz gauge will be identical to the Coulomb gauge in a specific case. What is that case?
When the derivative del dot j goes to 0.
What goes to 0?
Del dot j goes to 0. Like the second term, the derivative.
Coulomb gauge is divergence of A is equal to 0. Lorenz gauge, Lorenz with Z, not T, is the divergence of A plus, minus 1 divided by C square, derivative of phi with respect to time equal to 0. When these two they will be identical?
When the scalar potential is constant for time?
Is not time dependent. Exactly. So yes, they are the same, but you may find a coordinate which scalar potential is not time dependent. If you find that coordinate, it's fine. Moreover, if you write, let's go and review those equations. If you want, we can do it together, okay? But if you do a little bit of mathematics and look at the Lorenz gauge and Coulomb gauge, you will see very explicit that for the case of Lorenz, for the scalar potential and for vector potential, both of them, they follow wave equation. While for Lorenz gauge, scalar potential follows Gauss law, right? Which again, the same story, because there is no time dependency on phi. Then the second derivative of phi with respect to time is 0. Then you have again what we call a Laplace equation. So essentially, it's just a choice of freedom that you have. It's nothing really strange, but Lorenz gauge is more general, I would say. Okay, any other questions, guys? If you want, we can review that, because those are very important questions, and we need those gauges when we do the second quantization.
Which are the other two gauges? I don't remember them.
Pardon?
Which are the other two gauges?
Oh, those one of them is when you fix the Z potential. So you assume that you have only a Z. The other one I don't remember really by heart, because no one really is using it. But there are 4 gauges. Maybe after the meeting, I will send you an email.
Yeah,
Okay.
I just don't remember them. I mean.
Sorry, guys, having coffee. And if there is no other questions, we will start. Fine.
So, another question
Yes.
regards the plus and minus signs in the Lorenz gauge equation. Can we see them again? And because maybe I lost one minus sign.
So those people that they have already taken courses with me, they know very well that intentionally I add some negative mistakes. Very good, Valerio. Good point. Okay. Right, guys, do you know that? You got me. Okay, good. Excellent point. You get 1 mark. So for those people that they don't know and they have not taken courses with me, I intentionally do simple mistakes. And those simple mistakes is only for the people that they will pick it up. If you pick it up and send it to me, then you will get 1 mark. Okay? On the top of, let's say, 100. Good. Excellent. No other questions? Agreed, guys? Shall we start? Okay. So we reached to the point that we got Maxwell equations in the covariant form, and I say that go home and prove to me that the covariant form will result in the 4 equations that we know very well. So, and remember that those forms, they were derivative of alpha of if alpha beta equal to mu 0 j beta. And remember that this has j, and j, they were current, 4 currents. And what are the equations that they have current in the Maxwell equations? One of them is divergence of E is equal to rho divided by epsilon naught. And the other one is curl of B is equal to mu 0 j plus mu 0 epsilon 0 derivative of E with respect to time. Okay? Those are the 2 terms, the only 2 terms that they have rho and j in. Okay? Even with the blind eyes, I could say that that equation should give me these 2. And the other 2, which is derivative of alpha, let me remember, I don't, okay, yes. Derivative of alpha, 1/2 of epsilon alpha beta gamma delta, f of gamma delta will give me 0, then those 2 equations will give me the divergence of B is equal to 0 and curl of E equal to minus time derivative of B. Fantastic. So we knew that. But remember, from the relativistic regime, now we understood how I can get a field and how can I transform them from one coordinate to another coordinate. And physics is the same. The Lorenz force is a Lorenz force. Nothing will change there. Okay? The 2 observers, they will see exactly the same physics. They may see different component of electric field and magnetic field, but that's fine. Nothing is strange there. All right, good. We will come back and we will be using Maxwell equation. But no, maybe let's do that. Let's just solve them in a nice way, in a way that we know and we have seen it in electrodynamics. Divergence of B is equal to 0. What does it mean? That B is given by curl of A. Of course, we knew that. Previously we had these equations. If you remember, we look at the Bx, By, and Bz, which they were, if I remember well, they were F given by F alpha beta. And from those F alpha beta, you can calculate what is the derivative of alpha beta minus derivative of beta alpha. But it's exactly the same format, with just I'm expanding them. I'm looking at the physics. So, and also, what I know that curl of E is equal to minus time derivative of B, and B is already given by curl of A, then I will replace it here. Then you will get curl of E equal to minus time derivative of curl of A. Then if you do a little bit of mathematics, you will get curl of E plus curl of time derivative of A equal to 0. And for those people that they know, we can swap curl and time derivative if A is a well-behaved function, which we assume that the potential has this property. The derivative is well-defined. So, and taking the curl out, you will get curl of E plus time derivative of A equal to 0, and curl of a vector is given by 0, then that vector is given by a gradient. So for the convention, we choose that to be minus gradient of phi. So E plus time derivative of A is equal to minus gradient of phi. And from here, I will get E is given by minus gradient of phi minus time derivative of A. We knew this as well. We got it from F mu nu. So just I'm writing as an explicit, just to review what are those relations. All right. So this is for Eric. Replace, and now I have used only these two equations. I got B, which is given by curl of A. And from here, I got E, which is given by minus gradient of phi minus time derivative of A. And from these two, I can replace these two equations inside of the other two equations, which they are for current and the charge density. And I get a wave equations with a source for A and phi. Let's do that. Divergence of E is equal to rho divided by epsilon naught. And from here, let's replace divergence of minus gradient of phi minus time derivative of A equal to rho divided by epsilon naught. And then divergence of gradient, it will be Laplacian, so minus Laplacian of phi minus time divergence of A equal to rho divided by epsilon naught. All right. Replacing on the other equation, which is a curl of the other equation that we had was curl of B, which is plus mu 0 J plus mu 0 epsilon 0 time derivative of E. Okay. And we replace B with a curl of A, and we E with minus gradient of phi minus time derivative of A. And if you replace all of those equations, what you will get curl of A equal to mu 0 J plus mu 0, that will be negative sign, minus mu 0 epsilon 0 time derivative of gradient of phi plus time derivative of A. So curl of A, let's do the expansion. And using backup, so you will get gradient of divergence of A minus Laplacian of A equal to mu0j minus mu0 epsilon 0. Then you will get gradient of time derivative of phi plus minus mu0 epsilon 0 second derivative of time of a. All right. Nothing strange. Let's sort them properly. I will take minus Laplacian of a plus mu0 epsilon 0 is 1 divided by c squared time derivative of t of a equal to mu0 j. Then what I have here, I have minus gradient of divergence of a plus 1 divided by c squared t phi. Okay. So I got two equations. One is here. One is here. And then we can work on those two equations. Okay. So now you will see the two gauges, guys. Let me write the two equations. Those two equations, we call them equations for potentials with the source. All right. And I assume that the environment is homogeneous, and I assume that is vacuum essentially with source only. So I have minus Laplacian of phi minus time derivative of divergence of a equal to rho divided by epsilon naught, and the other equation is minus Laplacian of a minus plus 1 divided by c squared second derivative of t a equal to mu0 j minus gradient of divergence of a plus 1 divided by c squared time derivative of phi. Okay. Some people, I mean, usually when I sort them, I will write them differently just to clarify what I mean by these equations and see them in a proper format. Let me see if I can write that one the proper way. Yes, I think I can write them proper way, but anyway, let's do that. So the first gauge that we deal with is divergence of A is equal to 0, right? We call these Coulomb gauge. We know very well. If it's a Coulomb gauge, then the first equation becomes minus Laplacian of phi equal to rho divided by epsilon naught. True? Here, the divergence of A will be 0. Then I will get this equation. What I will get from the other equation, this is 0. Then I will get minus Laplacian of A minus plus 1 divided by c squared time derivative of A equal to mu0 j minus gradient of 1 divided by c squared time derivative of phi. Okay. This is the first equation that I have. Now, let's set the other gauge. The other gauge will tell me the divergence of A plus 1 divided by c squared time derivative of phi is equal to 0. This is Lorenz gauge. It's Coulomb. Now let's do that. So choose the Lorenz gauge and replace it inside of those equations. Divergence of A is replaced by this. Then the first equation will be minus Laplacian of phi plus 1 divided by c squared time derivative of phi equal to rho divided by epsilon naught. The other one, the entire the right side, the gradient will be 0. Then you will get minus Laplacian of A plus 1 divided by c squared time derivative of A equal to mu 0 j. Or better, write it in this way. Laplacian of phi minus 1 divided by c squared time derivative of phi equal to minus rho divided by epsilon naught, and Laplacian of A plus minus 1 divided by c squared time derivative of A is equal to mu 0 with a negative sign j. What are those equations, guys?
Wave equations.
Exactly. With
sources.
With sources. Beautiful. That's the reason that Lorenz force and Lorenz gauge is beautiful, because Lorenz gauge automatically will give you equations for potentials, which indeed they are waves and they are invariant under the transformation. Okay, this is the reason that most of the people they use a Lorenz gauge. Okay, good. All right. Now let's do a little bit of trick and see, or maybe I have to do something else before. Yeah, let's do something else before going to in deep calculation for Maxwell equation. So so far, what we learn is that you can have some sort of transformation, which those sort of transformation will give you the same physics. And we know how this transformation will apply to different quantities like position and time, velocity, what is happening with momentum and energy, what is happening with the current and with the potentials and with field. Okay, and we derive what are the Maxwell equations from those relations. Now I can still work with Maxwell equations and driving you something very interesting, which they call it Riemann-Silberstein equation. Or I can tell you why this is important. Let's go first with something which is what we call it first quantization, and just see if you can refresh your mind and follow me with some of those questions. So in the quantum mechanics, look, I'm not talking anymore about relativistic regime. I'm talking about the quantum mechanics regime now. So in the quantum mechanics, any quantities that we have, any systems that we have, we assign a wave function to it, right, guys? Which is psi. How do we find this psi? This is a quantum system. And this quantum system has an environment. And these two may interact with each other. How do I find the wave function for the quantum system?
Schrödinger equation.
Okay. Who said that?
Me.
Oh, Eric, yes. Any other thoughts, guys?
Probably set some boundary conditions.
Boundary conditions, yes, we do have boundary conditions, definitely. Any other thoughts, guys?
Assign the potential.
Yeah, a potential will be given by the interaction between the quantum system and environment. Right? Any other thoughts?
For relativistic stuff, we need to use the Dirac equation.
Who say that?
Josh.
Josh, yes, excellent. So first you have to look which regime you are looking into and what are the conditions there. If it's the relativistic regime, you have to go and solve the Dirac equation. If it's non-relativistic, then you have to go and solve Schrödinger equation. How many people they know Dirac equation? How many people they don't know Dirac equation? I just say, because I don't see all of you guys.
I don't know it.
Okay, good. So whom else?
I also don't know it.
I don't know it well.
Yeah, I also don't know it.
Good. So let's see how people they think about the Dirac equation. It's a proper, by the way, proper strategy, Josh. You are totally right. We have to look what regime we are looking into. But there is something more and more interesting behind the Dirac equation. Let's start with what Eric and Ben they said to me. They say to me, solve Schrödinger equation. What is Schrödinger equation? Is there anyone that doesn't know Schrödinger equation? Just say loudly or write in the text. Okay, I assume that everyone knows what Schrödinger equation. I assume that is a free particle. I don't have a potential here. Okay, environment is far away that doesn't interact. Oh gosh, there is something very interesting with this equation. Can you tell me what is the interesting part with this equation? You have time derivative, and what you have here? Derivative with respect to coordinate, right? Are they the same order? No. What? They are not in the same order. But I just learned from relativity that the time and coordinate, they are identical. They are the same. How is happening that in the quantum mechanic, time, the first derivative will appear, and coordinate, the second derivative will appear. So that's a puzzle. And then very unpleasant puzzle. How do we drive Schrödinger equation? How do we drive from classical mechanics to quantum mechanics? How do we do that?
I thought the Schrödinger equation was a postulate.
Not necessary. Yeah, you can assume that, but no. Everything comes from a fact. Let me do that. Who can help me with this?
I mean, you could consider the Hamiltonian first, and then like Hamilton's kind of like classical from Hamilton's equations, and then maybe like the Hamiltonian formulation, and then assign operators to.
Oh, you are very close, Arman. Yes, you are right. So assign operators. You can go very deep and go into a Hamilton equation, Jacobi Hamilton equation, or Lagrange equation, or whatever you wish. But you're totally right. This is one way. But what are the others?
To make the system discrete?
Yes, of course.
I think you should think about the de Broglie relations.
That's another perspective. Good. I like your thoughts, guys. Yeah. Seems that you learn very well. So Yaswan says that, okay, use E equal to P power of 2 divided by 2m and replace E, P with operators. Beautiful. Exactly. So what is the energy? Is kinetic energy plus potential energy. All right, guys, do you agree with me? Kinetic energy plus potential. Do you agree? Any objection? Okay. Now, energy is given by, what is the kinetic energy? P squared divided by 2m plus the potential, which usually potential is a function of x. All right. Now, the transition from classical to quantum is replacing everything with an operator. Energy is replaced by an operator. Momentum is replaced by an operator. And V is replaced by an operator, which is essentially X is replaced by an operator. Good. What is the energy operator? Who remembers this?
Hamiltonian?
Ah, come on.
It is IH bar d by dt.
What?
IH bar.
Exactly. IH bar time derivative. And what is P?
The grade, something times the gradient.
Minus I H bar the gradient. Okay, now let's write this. So energy times psi of x and t is given by P squared divided by 2m plus V x times psi of x and t. And now if you replace those operators, then you will get I h bar time derivative of psi of x and t. This is given by minus h bar divided by 2m Laplacian plus V of x psi of x and t. This is what we call it the naive way of thinking, that you can replace these. But Arman, you say it correctly. You can go with Hamiltonian, and then you can do the proper quantization. Okay, but this is way. I mean, it works. It works. I mean, it's a naive way, but you can see that how we can get the Schrödinger equation. This is one of the reasons that always people they puzzle with the foundation of quantum mechanics. Good. Any questions? So I think you understood, guys, that we have problem with Schrödinger equation. And the problem is that time and position, they are not treated equally. While relativistic regime will tell us that time and position, they are identical. Do you agree with this statement?
Yep.
Okay, good. Then we have to build up another equation. Let's do that. Let's do it together. So did you see that how I built up that equation? I started from energy, and from energy, I replaced energy and momentum with their operators.
But it's not like they're like treated unfairly. It's like if the energy is not so big, they're different.
Of course. I mean, we know that the relativistic regime always will give you the result in the classical way if the difference in energy is not huge. We know very well. Of course, you are right. Do you remember that I derived this equation for you?
Yep.
I say that in relativistic regime, energy power of 2 is equal to P squared C squared, right? Plus M0 power of 2 C4. I got it from P alpha, P alpha. Do you remember that? Okay. Now let's do that. Replace E with the operator. Make it operator first. So you have E squared. You have P squared C squared plus M0 power of 2 C power of 2. Those are scalars. Sorry, power of 4. And then I will have E squared psi of x and t is equal to P0 C squared plus M0 power of 2 C power of 4 psi of x and t. All right. Now energy will be replaced by I h bar, time derivative, and momentum will be replaced by h bar divided by I gradient, or minus I h bar, it doesn't matter really. And then what we will get, do it by yourself and see what you will get out of these equations. So you will get minus h bar squared, second derivative of time. Wow, beautiful. I get second derivative of time of psi of x and t equal to minus h bar power of 2 Laplacian times c squared plus m0 power of 2 c power of 4 acting on psi of x and t. Set it up together. I will get h bar power of 2 c squared Laplacian minus h bar power of 2 time derivative of psi of x and t equal to m0 power of 2 c4 psi of x and t. Okay, let's divide both sides with h bar power of 2 c power of 2 and then simplifying this. So that will be Laplacian minus 1 divided by c squared time derivative and then psi of x and t equal to m0 power of 2 c power of 2 divided by h bar power of 2 psi of x and t. And if you recall this, alpha was 1 divided by c squared times square minus Laplacian, which I call that D'Alembert or D'Alembert, something like that. Sorry for the pronunciation. And then that means that equation that I get minus sign, I bring it to the other side, it will be positive. So I will get this equation. Okay. Who knows this equation? Anyone?
I don't know anything more than what it's called. The Klein-Gordon equation?
Exactly. They call it Klein-Gordon equation.
If you want to be like really formal, is Klein-Gordon Fock equation.
Yes.
Don't forget the Russians. They're nice sometimes.
It is recorded. Manuel. It's not look like the lecture which we can have jokes.
We can have jokes. I can just get fired.
Okay, so that's the Klein-Gordon equation, and note that the Klein-Gordon equation is fully relativistic. Look at the orders of derivatives here. Second derivative of time, second derivative of position. That's beautiful. This does not look like the Schrödinger equation because it treats both time and position exactly in the same way. And this is described for scalar field in the relativistic regime. Whenever you neglect the polarization, you neglect the helicity, you neglect the spin, this is the equation that you describe. Either is electron, is photon, is neutron, the mass will be replaced here. Okay? What is the rest mass for photons?
Zero.
Zero. That gives you the wave equation that you had it. What is the rest mass for electron? Put it there. You will get the scalar wave equation for electrons, and etc. So remember, this is extremely useful and is fully relativistic. Okay? Is much richer than the Schrödinger equation. Okay? It also covers the regime which you go with higher than which you go close to the speed of light. Okay? Look at this term. C squared is a big number. 1 divided by h bar square is a big number. But if your rest mass is small, okay. Good. Any questions so far? Is not the end of story. Why? Because a genius scientist or a genius engineer say that, look, I don't like this. Still, I believe that the equation should be the first order, not second order. Dilip is not here because Dilip likes this guy. Is Dirac, Paul Dirac from Bristol. He said that, okay, it's fine. And by the way, Schrödinger also got these equations. And he assumed that energy is low, and then approximately he got his Schrödinger equation. So if you assume this, that the energy is low, then approximately you will get the Schrödinger equation. Nothing is wrong with that. But this is more general. So Dirac says, okay, that's totally fine, but let me tell you something more. I don't like that this is a second order derivatives. Is there any way that I get this equation? Let me expand this equation. Or let's go with the first one here. Let's expand it. So I will get second derivative of x, second derivative of y, plus second derivative with respect to z, minus 1 divided by, oh, let's do something else. Okay, I will write it in this way. Ct, I'm sure that you understand what I mean, of psi of x and t equal to m0 square c square divided by h bar square of psi of x and t. Okay. So Dirac says that let's take this operator and write it down in terms of product of two additional operators. So let's write down as A derivative with respect to x plus B derivative with respect to y plus C derivative with respect to z. Since we have a negative sign, we have to go with an imaginary plus I d derivative with respect to ct, derivative with respect to ct, times A derivative with respect to x plus B derivative with respect to y plus C derivative with respect to z plus I derivative with respect to ct. Of psi acting on psi and t equal to m0 square c square divided by h bar square of psi of this. Okay, did you get the idea? So he said that let's not work with the second order derivatives, but let's work with the first order operators, but the product of these two. So he assumed that A derivative with respect to x plus B derivative with respect to y plus C derivative with respect to z plus I derivative with respect to d times ct acting on psi will give you another parameter, which I call it, I don't know, maybe alpha, yes, of psi. And he said that let's act this operator twice, then what I will get A derivative with respect to x plus this one power of 2 acting on psi is given by alpha square of psi. So alpha definitely is given by m0 c divided by h bar. And then instead of working with Klein-Gordon equation, I will work, or I will deal with the first order derivatives of time and space, which means that I am now dealing with A derivative of x plus B derivative of y plus C derivative of z plus I d derivative of ct times psi, which is given by m0 c divided by h bar psi.
Quick question.
Of course.
Is alpha supposed to be I m naught c over h bar? Because when you pulled the m naught squared c squared over h bar squared over, you forgot a negative sign, I think.
Let me see. The equation is written properly, right? Oh, yes, yes. Thank you. Here is a negative sign. No,
yeah.
No, that's correct.
It's in front of the m naught squared c squared over h bar squared. No?
Here, you mean?
Yeah, right there.
So look, I got it from the upper equation.
Right.
Which that equation comes from this one. True?
Oh, okay. I see. Okay, never mind then. Thank you.
It's fine.
Yeah.
Okay, let's make the product of these, right? What it should be the result of these two terms if I want to do the product. You know, I highlighted them with red or now yellow. Look, I make a product of these two. What I should get if that assumption of algebraic approach is proper, what I should get. I should get Klein-Gordon equation, right? I should get that equation. Is that true? Because this is the assumption. We say that we have these second order derivatives. We split them in terms of two operators, which when you make the product, then you will get the same equations. Now there will be conditions on A, B, C, and D. Okay? So what is happening? First, you will have this term, making a product of that one. You will get A squared. Then A squared should be equal to 1, because that's the coefficient that you have. Then you have A times B, which is the cross term. You have derivative of x, derivative of y. And then also you have B times A, which is B, A, derivative of y, derivative of x, which the sum of these two should be equal to 0. Then from that relation, you will get conditions or restrictions on A, B, C, and D. What are those relations? You will get A squared should be equal to 1, B squared should be equal to 1, C squared should be equal to 1, D squared should be equal to 1, and A times B plus B times A should be equal to 0. A times C plus C times A should be equal to 0. B times C plus C times B should be equal to 0, and etc. A times D plus D times A should be equal to 0. D times B times D plus D times B should be equal to 0. And finally, C times D plus D times C should be equal to 0. I think I missed something, or is it all okay? So those are the conditions that I have for A, B, C, and D. Now let me ask a question. Who wants to be a volunteer for this question? Who wants to be? Tenglo?
I'm sorry, I not too clear, so I cannot give you an answer.
The question that I have, Tenglo, is that A squared is equal to 1, B squared is equal to 1, C squared is equal to 1, D squared is equal to 1. But A times B plus B times A is equal to 0. Do you have any guess on the form of A, B, and C? And D, of course. Tenglo?
I'm sorry, I'm still thinking.
Okay, no worries. Whom else? Look, what are the numbers which when you make a square, they will be 1. But when you look at the product of them, they don't commute with each other. Look at that equation. Is A times B plus B times A? No. A times B, look, Reza says that is 1 and I. Assuming that A is equal to 1, B is equal to I. Look, that is true that the power is -1, of course. I mean, there is a problem there. But even look at that. A times B plus B times A is 1 times I plus I times 1. That definitely is 2I.
Oh, I see. Okay.
Do you know what I mean?
They have to be of opposite signs. It's like 1 minus I.
No, I'm not looking for the sign. I'm not looking for the numbers. Something else, something. Just tell me what.
Quaternions?
What?
Are you looking for quaternions?
Close, but it's much easier than that.
Matrices?
Okay. Exactly. Those should be matrices, because the matrices, they will not commute.
These are the Pauli matrices?
Oh, yes, that's excellent. That's excellent. Who said that, Henry?
Yeah.
Beautiful, Henry. You got that. But even before going there, you can ask yourself, how is possible that A times B doesn't commute with each other? So A and B, they don't commute, but A times B plus BA is equal to 0. So then you will come out with an idea that A, B, C, and D, they should be matrices. And then you have to look for the form. And that's the beauty of Pauli matrix, Dirac equation. So if you do the calculation, what it shows up that A, and let me write it down for you guys, erase this. A is identity matrix. Essentially, that should be a 4x4 matrix. Okay, I'm only writing the 2 terms. So let me, first of all, let me write it down in a proper way, and then I will tell you what I have as an assumption. So it should be like that. These terms are 0. Then I have 1, 1, 0, 0. Oh, sorry, that should be -1, -1. That should be 1, 1. Okay. These are the matrices that I have. But for simplicity, since we know that it's 4x4, and each of them, they can be sorted as 2 groups of matrices, so we write them as in this way. Identity matrix minus identity matrix, and those are 0. And B is given by 0, 0, sigma x minus sigma x. C is given by 0, 0, sigma y minus sigma y. And D is given by 0, 0, sigma z minus sigma z. Okay. Let me write it properly. There is an I coefficient at the front of all of them. I here, I here, I here, I here. All of them is positive. D doesn't have anything. Good. Okay. As an exercise, you can do it at home. These are the matrices that you have, and you have this equation. Prove that this equation power of 2 will give you Klein-Gordon equation. So check these out, please. In a couple of minutes, I will finish. And then, and by the way, why we are reviewing Dirac equation, not this is only the beauty of Dirac equation that is in agreement with relativistic regime, but you will see in next lecture that we will find an equation for light which is very similar to Dirac equation and is Riemann-Silberstein equation. And you will see that why we are avoiding the word of wave function for light. We will discuss all of that in the next lecture and the quantization as well. So, however, at the end, if I want to write the Dirac equation will be simplified and it can be written in this form as I h bar. I call those equations, should I write them as, yes, I will write them gamma in the standard form, gamma mu, derivative with respect to mu, minus m0c times psi. I will define what I mean by gamma. X and t equal to 0. And gamma matrices, gamma 0 is this equation, gamma 1, that should be gamma 0 should be 1 and minus 1, gamma 1 should be, sorry, gamma 0 should be sigma x because it's that one is sigma x, because it's related to the time, sorry, sigma z, negative sign, that is 0, sigma 1 is 1 and minus 1, sigma 2 is 0 and sigma x, sorry, sigma x, and gamma 3 is 0, sigma y with negative sign. So that's what we call it a Dirac equation. You may see it in different form as well. So Feynman uses another notation. So he called gamma mu derivative with respect to mu, which appears in most of the calculations, as d slash. Okay. So then that can be given as I h bar d slash minus m0 c psi of x and t. Now you will see that in either of those equations, here or here, time and space, they are treated equally. And you will get an equation which is follows the relativistic regime. Okay, so now remember, just to conclude, so far we started from relativistic regime, we treated the field, we got Maxwell equations, and also we look at the matter waves, which is a Klein-Gordon equation. And we say that in the relativistic regime, also you can get what we call it Dirac equation, which time and space, they are treated equally. And remember, we call this section first quantization, because we get wave equations for a particle which has a mass. You will see always we have m0 in all of those equations. So when we deal with matters, we can quantize the wave function for the matter, and we call these the first quantization. However, this doesn't apply to electric field and magnetic field, because electric field and magnetic field, they don't have a rest mass. you cannot find a frame which photon is stationary there. So photon, if you do any transformation, always photon will travel with the speed of light, assuming that is in the free space. There we have to do the second quantization. What we do, the wave function will be quantized on the top of this. And next lecture, we look at finding wave function for photon, and we will compare that with the Dirac equation. That's the reason that I talk about Dirac equation. And we talk about the helicity, and then we will do the field quantization. And from field quantization, it is extremely simple to follow. So do you have any questions, guys? No? Okay, I see that all people almost, they have camera on, except Tenlong. Tenglu, sorry. Yes, sorry, I know that you're working in the lab. I will stop recording now.